The lead went over the side and touched nothing. 200 fathoms of line, no bottom, while weeds stretched to the horizon, and every man aboard swore they were aground over a drowned meadow. Under the keel, 3 miles of water. This is the Sargasso Sea, the only sea on Earth with no coastline, held by 4 currents. The weed never trapped a ship. The windlessness did. That answer is incomplete, because the same slow convergence that stalls a vessel also swallows the evidence when one is lost. So why is there never wreckage? 1492, 1609, 1872, 1918. Still now, 4 dates, a crossing that nearly turned back, a flagship torn apart by a hurricane, a brigantine found sailing with nobody aboard, and a warship that took 309 people with her. Different centuries, different ships, different failures, and one shared property. Almost nothing came back. What they also share is stranger. The only solid ground anywhere inside this entire system is one small island, and that island has wrecked more vessels than the thousands of kilometers of open water around it. Start with the lead, because the lead is where the misreading begins. For 4 centuries, a sounding line was the only instrument a sailor had that could tell him about the world below the waterline. A shaped lead weight, a line marked at intervals with leather, calico, and knotted twine, so you could read depth by feel in the dark, and a hollow cup in the bottom of the weight packed with tallow. You threw it, you let it run, and when it struck you hauled it up and looked at what the tallow had brought back. Sand meant one thing. Broken shell meant another. Gray mud meant you were somewhere specific and could say so on a chart. A lead line that found bottom was information. A lead line that found nothing was silence. And weed, to any seaman of any nation, meant shallow water. Weed grows on rock. Rock near the surface means a bank. And a bank means land, and land in the middle of an ocean crossing means you are somewhere you did not plan to be, at speed, with no way to see what is under you. That inference is not stupidity. It is the single most reliable rule of thumb in coastal navigation, and it had kept ships off rocks from the Baltic to the Gulf of Guinea. The Sargasso Sea takes that rule and turns it inside out, because this weed does not grow on anything. Sargassum natans and Sargassum fluitans are holopelagic. They complete their entire life cycle floating. They never anchor to a seabed, never send down a holdfast, never touch stone. They reproduce by breaking apart, each fragment continuing to grow, so a single mat can in principle be an unbroken lineage drifting for years. Little gas-filled bladders the size of peppercorns keep the fronds at the surface. What a sailor read as the roof of a shoal was a raft, with several kilometers of open water underneath it. Now widen out, because the shape of this place is the reason everything else happens. Every other sea on the planet is defined by land. The Mediterranean has Europe and Africa. The Caribbean has an arc of islands. The Red Sea has 2 deserts. The Sargasso has nothing. Its boundaries are moving water, the Gulf Stream running up the western edge, the North Atlantic Current carrying that flow east across the top, the Canary Current sliding south down the eastern side off Africa, and the North Equatorial Current closing the loop westward along the bottom. 4 currents turning clockwise, and the still region they enclose is the Sargasso Sea. It sits between roughly 20 and 35 degrees north and 40 and 70 degrees west. Draw a rectangle at those dimensions, and you have covered about 3.5 million square kilometers, which is a shade more than the entire area of India, in a part of the Atlantic where you can sail for a week and see nothing but water and weed. That is a border made of motion. It shifts. It breathes with the seasons. There is no line you cross, no light you raise, no bearing you take. You know you have arrived because the wind dies and the water changes color. The color is the second warning nobody could read. Sargasso water is famously, almost aggressively blue, and it is among the clearest open ocean water measured anywhere, with underwater visibility recorded to around 60 meters. That clarity feels like a gift. It is a symptom of starvation. Here is the chain, and it is worth getting exactly right, because everything that happens to human beings in this sea comes out of it. Sitting over the region, most of the year, is a semi-permanent zone of high pressure, the Bermuda Azores High. In a high, air descends. Descending air warms as it is compressed, and warming air can hold more water vapor before any of it condenses, so cloud evaporates instead of building. The result at sea level is a large area of light, variable, unreliable wind, and very little rain. That is the calm belt. Sailors called those latitudes the horse latitudes, and the calm there is not the pleasant flat water of a summer afternoon. It is days of glassy swell, with sails slatting against the masts, the ship rolling and making no way at all, the compass cards swinging, while the wake dies out astern. The same wind pattern does something else, and this is the part that takes a moment to see. The trade winds blow from the northeast across the southern part of the gyre. The westerlies blow from the west across the northern part. Because the earth rotates, water pushed by wind does not travel in the direction of the wind. It is deflected to the right in the northern hemisphere, and the net movement of the wind-driven surface layer ends up roughly 90 degrees off the wind direction. That is Ekman transport. And in the North Atlantic subtropics, it means the trade winds push surface water to the north, and the westerlies push surface water to the south, and both of them are shoving water toward the same central region. Water piles up. Not dramatically. The center of the gyre stands measurably higher than its edges, on the order of a meter, which is nothing you would ever see from a deck and everything to the ocean. Piled water has to go somewhere, and it cannot go outward fast enough, so it goes down. That downward push, sustained over decades and centuries, presses the boundary between warm surface water and cold, deep water far below the sunlit layer. In the middle of this gyre, the nutrients that feed every food chain in the ocean sit hundreds of meters too deep to be reached by light. None of that was visible to anybody standing on a deck. A meter of extra sea surface height spread across 1,000 kilometers is a slope so gentle that no instrument carried by a ship could detect it. And for most of the history of this ocean, the entire mechanism was an inference from wind patterns and water temperature. The mound was finally measured directly from orbit. Satellite altimeters, beginning in a serious way with Topek Sias Poseidon in 1992, bounce radar pulses off the sea surface and time the return precisely enough to resolve height differences of a few centimeters across an entire ocean basin. Put that data on a map of the North Atlantic, and the gyre appears as exactly what the theory predicted: a broad, shallow dome of water standing higher in the middle than at the edges. Since 2000, autonomous floats drifting in the interior have filled in what is happening underneath, sinking to a kilometer or two, then rising while recording temperature and salinity, and surfacing to transmit. What those instruments describe is a slow, permanent downward push in the center of the gyre and a warm surface layer sitting on top of a boundary that will not break. So nothing grows, or almost nothing. The plankton that would normally cloud coastal water is largely absent, and without plankton the water stops scattering light, which is precisely why it is so blue, and why the eye reaches so far down into it. Oceanographers call these regions oligotrophic. The blunter description used for decades is the blue desert. Now put a human being in it. You are becalmed. It is 30 degrees on deck, and the sun is directly overhead. There is no wind to move you and no wind to cool you. There is no rain, so the canvas rigged to catch fresh water stays dry day after day. You put lines over the side and catch nothing worth eating, because there is nothing there to catch in any quantity. You can see 60 meters down into water you cannot drink. Your fresh water is in casks, and casks were filled to a schedule based on an expected passage time, and your passage time is now unknown. That is the actual weapon, not weed, not currents, arithmetic. The number of days of drinking water divided by the number of days it takes for the wind to come back. And the crews that survived this water were the ones who had stopped treating the ocean as a distance to be crossed and started treating it as a machine with a shape. The Portuguese worked that out first over most of the 15th century, and it cost them decades of dead sailors to learn. Sailing south down the African coast was straightforward, because the wind and current went that way. Coming home was close to impossible, because you were beating into the same northeasterly trade wind that had carried you down, tacking for weeks, running out of food. The answer they eventually built into their navigation was completely counterintuitive. To go home to Lisbon, sail away from Lisbon, head out west and northwest into the open Atlantic, far from any land, out into the middle of the ocean, until you climb far enough north to pick up the westerlies, and then let those winds carry you home. That great looping arc was called the Volta do Mar, the turn of the sea. It is one of the most sophisticated pieces of environmental observation in the history of navigation, and it exists nowhere as a theory. There was no concept of a subtropical high, no Ekman transport, no gyre. What existed was a route, passed pilot to pilot, that encoded the entire circulation of the North Atlantic as a set of instructions about where to point the bow. Those pilots knew the calm center was there. They knew you went around it. They had no idea why. That is the difference that decides who dies out here. Adapting to the system means accepting that the shortest line on the chart is not the fastest line through the water, and that the ocean has a grain you sail along. Forcing an external schedule onto the system means running the straight line into the middle, because the calendar says so. Which brings us to a man who did exactly that, deliberately, on purpose, as the whole point of the voyage. In August 1492, 3 ships left Palos, dropped down to the Canary Islands, and then turned west and kept going west. Columbus was not exploring in the wandering sense. He had an objective and a theory, and the theory was that Asia lay a manageable distance across the ocean at that latitude. He picked the Canaries as his departure point specifically because the wind there blows steadily from the northeast, which meant a following wind, day after day, pushing him where he wanted to go. In terms of what he was trying to do, it was a good decision. The trades did exactly what he expected. The little fleet made excellent time. Then he sailed into the western edge of the Sargasso. The weed appeared around the middle of September. At first it was encouraging. Weed meant land. Land meant the crossing was nearly over. And after weeks of open water, the crews read those first patches as evidence that the theory was working, and Asia was close. Within days, the patches thickened into fields. The ships were sailing through what looked like a submerged prairie, mile after mile, weed brushing along the hull, weed hanging on the rudder. And the encouragement turned into something else. Because the calculation reversed. If weed meant land, and there was no land in sight, then the weed did not mean a coast. It meant a bank. It meant shoals, somewhere under the keel, which is the single worst thing to have under a ship making 6 knots in an ocean nobody has charted. They sounded. The line went down and found nothing at all. Somewhere in the debate that followed, both possible answers were bad. Either the sounding was wrong, and they were about to strike, or the sounding was right, and every rule they had about weed was worthless in this ocean. Columbus recorded the weed repeatedly in his log. Read the entries in sequence, and you can watch a professional navigator trying to force a landscape into a category that does not fit it. He describes vegetation that appears to come from rocks. He notes the direction it drifts from. He treats it as a sign of proximity to land more than once, and each time the horizon stays empty. The word we have to be careful about here is recorded, because the original is gone. The log Columbus kept aboard the Santa Maria did not survive. The manuscript disappeared sometime after 1504, and what we read today comes chiefly from an abstract made by the Dominican friar Bartolomé de las Casas, who worked from a copy owned by Columbus's son Diego, summarizing in places, quoting directly in others, and stitching the result into his own history. Scholars who have worked on it closely regard the Las Casas version as about as near the original as it is possible to get, short of finding the lost document. It is still unavoidably a copy of a copy, filtered through a man with his own view of events. When people talk about what Columbus wrote, that is the object they are talking about. Then the wind failed. This is the part that mattered most to the men aboard and matters least in the retelling. Somewhere in the weed, the following wind that had carried them west for weeks went soft and unreliable. A fleet that had been logging fine daily runs began drifting. And in a fleet where the crews were already frightened, already convinced that the weed meant shoals, already a long way past any distance they had ever sailed from land, the loss of wind was interpreted through the same broken rule as everything else. A sea that grew grass and would not let you leave red, to sailors, as a sea that had hold of them. Columbus was managing a crew problem as much as a navigation problem. He kept two reckonings of the distance run, the true one for himself, and a shortened one for general consumption, precisely so that the men would not know how far from home they had come. There is a straightforward reading of that. It is deception. There is another reading that sits alongside it. He understood that the crew's willingness to keep going depended on numbers they could tolerate, and that the truth would end the voyage. Both readings are about the same underlying pressure. Every day of calm ate provisions and produced no progress, and every day of no progress made the argument for turning back stronger. They got out. The calm here is patchy, not permanent, and the wind returned before the water ran out. On 12th October, they made a landfall in the Bahamas, and the entire subsequent history of the Atlantic follows from it. In terms of this sea, though, the important result is smaller and stranger. The first documented encounter between Europeans and the Sargasso Sea produced no deaths, no wreck, and no damage. It produced a misinterpretation. The sea's opening move was to hand experienced professionals a landscape that triggered every correct instinct they had and make all of those instincts wrong. That is survivable when the calm lasts days. Columbus was lucky in a way he could not have known. He crossed the outer part of the field in a season when the wind returned, with casks that had been filled recently in the Canaries. The obvious next question is what happens when the wind does not come back in time. And to answer that, we have to stop looking at single voyages and look at what happens when you collect thousands of them. In the 1840s, a United States Navy lieutenant named Matthew Fontaine Maury took over the depot of charts and instruments in Washington, a job nobody wanted, in a building full of old logbooks nobody had read. Maury had been injured in a stagecoach accident and was no longer fit for sea duty. What he did with the paperwork changed how the ocean was understood. He started pulling the logs apart. Not for stories, for numbers. Every day at sea, on every voyage, a ship's officers had been recording position, wind direction, wind force, current set, barometric pressure, sea temperature. Individually, each entry is trivial. Stacked by position on a chart, thousands upon thousands of them, they become a picture of the atmosphere and the ocean that no single observer could ever see. Then Maury did the thing that made it work. He printed his wind and current charts, beginning with the North Atlantic in 1847, and gave them away free to any shipmaster who agreed to keep a standardized abstract log and send it back. Captains got faster passages. Maury got data. By the 1850s, he had something like 1,000 vessels at sea simultaneously feeding him observations, and an international conference in Brussels in 1853 standardized the form so that ships of different nations were recording the same things in the same way It is the first large-scale crowdsourced dataset in the physical sciences, built out of self-interest, and it worked. Passage times fell. Some routes were cut by weeks. What the charts showed about the middle of the North Atlantic was a belt of unreliable wind that you should sail around rather than through. And what the logbook abstracts showed, entry after entry, was what actually happened to ships that ended up inside it. The recurring entry is not weed. It is water. The horse latitudes got their name from what happened aboard ships carrying livestock across to the West Indies. There are competing explanations for the phrase, and none of them is airtight. But the operational reality behind all of them is the same. A ship becalmed at 30 degrees north in high summer has a fixed volume of fresh water and an open-ended delay. Animals drink enormous quantities. Animals that cannot be watered die, and dead animals in a hold in that heat become a sanitation emergency. So they went over the side. Whether the phrase came from that practice or from something else entirely, the mechanism is documented across the age of sail. In the calm belt, the first thing that gets cut is water, and the first things that die are whatever is drinking it that cannot pull a rope. Rationing is a physical process with a schedule. You go from free access at the scuttlebutt to a measured issue, typically morning and evening. You stop washing. You stop cooking anything that requires boiling in fresh water, which means the diet collapses to salt provisions and biscuit, which increases thirst, which makes the ration feel smaller. Men working aloft in that heat lose several liters a day through sweat alone. You reduce work to reduce sweat, and reducing work means the ship gets worse at being sailed at exactly the moment you need her sailed well. Then people begin to steal, and the water butt gets a guard on it, and the guard is another man not doing seamanship. None of that is dramatic. It is a slow subtraction that ends with a crew too weak to handle canvas when the wind finally arrives. Now the part that should genuinely rearrange your understanding of this place. There is no force in the trap. Nothing out here grabs anything. The Sargasso does not pull ships in, and it does not hold them. The gyre circulation at the surface is slow and diffuse, a fraction of a knot in the middle. Nothing a sailing vessel would notice against even a light breeze. There is no whirlpool. There is no mat of weed dense enough to stop a hull, and there never was. The weed occurs in windrows and patches, and you sail through it, and it parts. Ships that went missing in this ocean were not held. They were delayed, or they were sunk, and those are entirely different problems. So if the calm cannot kill a well-found ship in normal conditions, what does? Two things. And they are both consequences of the same warmth that produces the calm. The first is that this is where hurricanes come to get strong and then turn. Storms form over the tropical Atlantic and track west, and a large fraction of them curve north and then northeast as they run into the steering flow around the western edge of the subtropical high. That recurving track carries them straight across the western Sargasso, over the deepest reservoir of warm water in the North Atlantic. Warm water is the fuel. A hurricane over a shallow, warm layer stirs cold water up from below and weakens itself. A hurricane over a deep, warm layer, which is exactly what the gyre's downwelling maintains, keeps drawing energy without cooling its own supply. So the same physics that makes the center calm, blue, and empty for most of the year makes the western side of it capable of sustaining an extremely violent storm in season. The still water and the storm are the same system seen at different times. The second thing is geography, and there is only one piece of it in the entire sea. Bermuda is roughly 53 square kilometers of land, sitting alone, more than 1,000 kilometers from the nearest continent. That is the island. The hazard is not the island. The hazard is the platform it stands on, a reef system, the northernmost coral reef complex in the Atlantic, extending well beyond the visible land, in places many kilometers offshore. These reefs rise from deep water almost vertically. There is no shelving approach, no gradual shoaling, no series of soundings that warn you. You can be in blue water with no bottom on the lead, and then be in coral within a ship's length. Now add the navigational reality of the age of sail. Latitude you could get reliably by measuring the sun at noon. Longitude, east and west, you could not. Not until the chronometer became affordable and widespread in the 19th century. So a ship crossing the Atlantic knew roughly how far north it was, and only estimated how far along it had come by dead reckoning, by log line and compass, and a running guess about current. Errors accumulated. A vessel could be 100 miles from where its master believed it to be at night in a rising sea. Put that together, and you have a single obstruction in an ocean the size of India, invisible until you are on it, sitting directly on the recurving track of Atlantic hurricanes, in the era when nobody could tell you exactly where they were. More than 300 shipwrecks have been documented on and around that reef platform, ranging from the early 1600s to the late 20th century. Bermuda is regularly described as having more wrecks per square mile of surrounding water than anywhere else on the planet. And while that kind of superlative is hard to audit precisely, the underlying count is not in dispute. 3 centuries of ships piled onto one small ring of coral in the middle of nowhere, all of which is the setting for the summer of 1609. And for the single strangest rescue in this entire story, because the thing that saved 150 people is the same reef that has broken hundreds of hulls before and since. The objective was simple and desperate. Jamestown, the English colony in Virginia, was failing. It was 2 years old, undermanned, badly supplied, and in conflict with the Powhatan Confederacy on whose land it sat. A relief expedition called the Third Supply left Plymouth in June 1609. With around 9 vessels and several hundred people aboard, carrying food, tools, and the colony's new leadership. The flagship was the Sea Venture, brand new, purpose-built, and carrying the men who mattered. Sir Thomas Gates, the incoming governor, Sir George Somers, the admiral of the fleet, and Christopher Newport, the most experienced Atlantic captain England had. They were sailing in July. That is hurricane season. And although nobody in 1609 had a concept of a tropical cyclone as a rotating system with a track, English mariners certainly knew that late summer in the western Atlantic produced storms of a violence they did not see at home. The schedule was not set by weather. It was set by a starving colony and a company in London that needed the colony to survive. The initial condition was control. A new ship, a strong fleet, a good crossing, and the flagship leading. On 24th of July, the weather went. What hit them was almost certainly a hurricane, and the fleet was scattered in the first hours. Sea Venture was separated from the others and left alone in it. The first warning aboard was not the wind. It was the water in the hold. William Strachey, a passenger, wrote a long account of what followed, the true reportory, and it is among the most detailed storm narratives to survive from the period. What he describes is a new ship coming apart at the seams, caulking working loose under the flexing of the hull, then leaks, then a rate of ingress nobody could locate. They searched for the breach and could not find it. That detail matters more than it looks. A leak you can find, you can plug. A leak you cannot find is a countdown. So they did the only thing available. Everyone aboard, passengers and crew, gentlemen and sailors, went onto the pumps and the bailing lines. 3 pumps working continuously. Bucket chains from the hold to the deck. Shifts of an hour on and an hour off, around the clock, for 3 days and 3 nights. Strachey's figure for what they moved is 2,000 tons of water from Tuesday noon to Friday noon. Understand what that means physically. They were not gaining. They were holding, barely, and each hour of holding cost them strength they would not get back. Men were falling asleep at the pumps. Some simply stopped and lay down where they were. Gates took charge of organizing the pumping. Summers stayed on the poop deck effectively without sleep, conning the ship for the duration. They threw cargo overboard to lighten her. They cut away the mainmast rigging. And still the water rose in the hold. By the morning of 28th of July, the water was around 9 feet deep inside the ship, and the effort had passed the point where it could be sustained. A crew that has been bailing for 3 days cannot bail for a fourth. The ship was going to sink in open water, hundreds of miles from anywhere, with 150 people aboard and boats capable of carrying a fraction of them. Then, Summers saw land. What Summers did next is one of the most clear-eyed things anyone does in this entire story. Bermuda, to an English mariner in 1609, was not a refuge. It was known, and it was avoided. Spanish and Portuguese ships had been wrecking on it for a century, and its reputation in English was the Isle of Devils, a place of noise, storms, and shipwreck that prudent navigators gave a wide berth. Summers was looking at the most feared obstruction in that whole ocean, and it was the only solid thing within reach of a ship that had hours left. He drove her onto it, deliberately. He put the helm over and ran the Sea Venture at the reefs so that she would ground and stick rather than founder in deep water. She wedged between 2 rocks about a kilometer offshore and held together long enough. Every single person aboard, roughly 150 men, women, and children, got off. Nobody drowned. Sit with that for a moment. In a sea with no shore, salvation was the coral that everyone competent had spent a century learning to avoid. The same geography that destroys hulls preserved people, in the same act, in the same minutes. It is not luck in the vague sense. It is a specific property of that reef. It rises to within centimeters of the surface out of deep water, which is exactly what makes it lethal to a ship underway at night, and exactly what makes it a place a sinking ship can be stopped on top of. And now the emergency changed shape entirely, because they were alive on an uninhabited island with no vessel. This is the thing modern readers underestimate. They were not marooned in the sense of waiting for rescue. Nobody was coming. The rest of the fleet had scattered and made Virginia assuming the flagship was lost, and England assumed the same. There was no signal to send. Their survival now depended on whether 150 people could build ocean-going ships from what an uninhabited Atlantic island and 1 broken wreck could provide. The island helped more than they expected. Bermuda had no permanent inhabitants and therefore no predators of consequence. And it had feral hogs left by earlier Spanish visits, immense numbers of seabirds that had never learned to fear humans, sea turtles, fish, and palmetto. They ate well. Strachey's account is full of the strangeness of finding abundance in a place whose entire reputation was terror. They also salvaged relentlessly: rigging, sails, ironwork, tools, planking, anything the wreck would give up. They cut Bermuda cedar, which is dense and rot-resistant, and turned out to be excellent boat timber. They also did not simply settle in and start building. The first plan was faster and far more dangerous, and it cost lives. Gates had the ship's longboat fitted with a deck and a mast and turned into something that could, in theory, sail 600 miles of open ocean. Henry Ravens, the Sea Venture's master's mate, took her out with a settler named Thomas Whittingham and 6 sailors aiming for Virginia to bring back a rescue vessel. The first attempt on 28 August 1609 failed before it began. They could not find a way out through the reef in the dark and came back. 2 days later, they got clear and headed west. Ravens gave the people on the beach a schedule. If he lived and reached Virginia, he would be back by the next new moon, meaning sometime in late September. The survivors agreed to keep a fire burning on high ground so he could find the island again on his return. They kept that fire lit for weeks. Somebody had to gather the wood. Somebody had to stay with it through the night. And every night that it burned was a night of watching an empty horizon for a small boat. The longboat and everyone in it were never seen again. 8 men in an open boat in the western Atlantic in September, in the middle of hurricane season, is a set of odds that does not need explaining. That failure is what forced the shipbuilding program. Once it was clear nobody was coming, the survivors stopped waiting and started cutting timber. It took 10 months. In that time, they built 2 vessels, the Deliverance and the smaller Patience. And the Enterprise nearly came apart repeatedly. There were at least 2 conspiracies against Gates's authority. There was a killing on the island and a death sentence that the man's shipmates overturned by hiding him. 2 babies were born and given the names Bermuda and Bermudas. Several people died. The social order of the expedition, which had been imposed by London and rank, had to be renegotiated by people who now needed carpenters more than they needed governors. On 10th of May 1610, the 2 new ships sailed. On 24th May, they reached Jamestown and walked into the starving time. The colony they had been sent to relieve had gone from several hundred people to around 60, and the survivors were in a condition that Gates found unsalvageable. He made the decision to abandon Virginia entirely, loaded everyone aboard, and started down the James River for home. They were met coming upriver by another relief fleet under Lord De La Warr with supplies and men, and turned back. The English presence in North America continued because of a coincidence of a few days. 2 men chose to stay behind on Bermuda when the ships left, and the island was formally settled from England within a few years, largely because Strachey's and others' accounts made it sound survivable rather than demonic. That account also went somewhere else. Strachey's report of the wreck circulated in London manuscript, and the storm, the island, the sailors, and the noise of it turn up shortly afterwards in a play about a shipwreck on an enchanted island. The Tempest is the most famous piece of downstream evidence in this story, and it exists because a ship was deliberately run onto a reef. The wreck itself was found again in 1958, identified and excavated over the decades that followed, lying in shallow water off the eastern end of the island, close to where the accounts said she had been driven. 3.5 centuries of legend, and the ship was exactly where the men who wrecked her said it was. The reef that held her did not stop being lethal when navigation improved. It stopped being lethal to ships that stayed away from it, which is a different thing. On 25 October 1936, the Cristobal Colon, a Spanish liner of just under 500 feet, 3 decks high, and one of the more luxurious ships on the Atlantic, ran onto North Rock, about 8 miles north of Bermuda. She was making something in the region of 15 knots when she struck. There was no storm. Visibility was not the problem it had been for 3 centuries of sailing masters. The reported cause was a misidentification, a light ashore taken for the Gibbs Hill Lighthouse, and a course laid accordingly. She is still there. Craichelu Chiesture Chilves, broken across a wide area of shallow water, and she remains the largest known wreck in Bermuda's waters. A steel liner with charts, lights, a compass, and a wireless set was defeated by the same process that had been killing ships on that reef since the 16th century. An approach with no shoaling water to warn you, and a position that turned out to be wrong. What the Sea Venture proves is narrow and important. In this sea, the vessel and the people are separate problems. You can lose the hull completely and keep everyone. And the reverse is also possible, which is the case we are about to look at, because 263 years later, this ocean produced the exact mirror image, an intact, seaworthy, fully provisioned ship sailing along under her own canvas, with nobody aboard at all. Between those 2 events, the Atlantic filled up. In 1609, a crossing was an expedition. By the middle of the 19th century, it was a timetable. Packet ships ran fixed sailing dates from Liverpool and New York, whether or not they had a full cargo, because reliability was the product. Emigrant traffic put millions of people onto the water. The cotton trade, the grain trade, the sugar trade, the guano trade, all of it crossed this ocean, and the routes were shaped by exactly the wind system Maury had mapped. Outbound from Europe, you dropped south to pick up the trades. Homebound from America, you ran north and east with the westerlies. The Sargasso sits in the middle of that circuit, like a roundabout that everyone drives around and a few people drive through. Steam changed the calculation without removing the sea. A steamer does not care about a calm belt, which meant that from the 1840s onward, it became possible to drive a straight line across the middle of the gyre and hold a schedule. That is a genuine improvement, and it created a genuine new exposure. Ships now routinely cross the emptiest part of the Atlantic, far from the sailing routes, where a mechanical failure left you in a region with almost no traffic and no way to tell anyone. Sail was slow and stayed where other ships were. Steam was fast and went where they were not. And the insurance industry that grew up around all this cared about one number: whether ships came back. Lloyd's kept the records. Underwriters priced risk by route and season. Cargo was surveyed, hulls were classed, and a vessel's loss produced paperwork, an inquiry, and money moving. That bureaucracy is the reason we can reconstruct any of these events at all. It is also the reason a particular kind of Atlantic disappearance became visible as a category. Ships that were properly insured, properly documented, and then simply did not arrive, with nothing ever recovered. That absence needs explaining, because it is the engine of every myth attached to this water, and the explanation is physical. Go back to the convergence. Surface water being pushed toward the center of the gyre from all sides does not just pile up. It drags everything floating in it along. That is why the sargassum is here at all. The weed grows and fragments across a huge area of the western Atlantic, and it ends up concentrated in the gyre, because the gyre is where floating things go. Anything buoyant that enters this circulation eventually gets swept toward the same latitudes. So when a ship breaks up, the buoyant remains of her get concentrated, which sounds like it should make the debris easier to find. It does the opposite for 3 reasons. The first is time. Concentration is not fast. Surface convergence in the open gyre operates over weeks and months, not hours. A search is conducted over days. In the window when anybody is actually looking, wreckage is doing the other thing, dispersing, driven by local wind and wave, and the differing drift rates of objects with different amounts of surface exposed to the air. A wooden hatch cover, a life ring, an oar, and an oil drum all move at different speeds and different angles from the same starting point. Within a week, they are tens of miles apart in an area with no landmarks. The second is that most of a ship is not buoyant. A steel hull with a cargo of ore goes down as a unit and stays down under several kilometers of water. What floats away is a small percentage of the total, mostly timber, cork, canvas, and light fittings. And in an ocean this size, that is a handful of objects scattered across thousands of square kilometers. The third is that the surface layer here does not hold things indefinitely. Anything organic waterlogs and sinks. Anything with a rough surface accumulates growth and sinks. Objects that stay up get slowly biofouled until they lose buoyancy. The gyre gathers, and then it takes things down out of the layer we can see. Put those together, and the result is stark. In this part of the Atlantic, a total loss with no survivors will very often produce no recoverable evidence at all. Not because something strange happened, but because of the specific combination of enormous area, deep water, slow surface convergence, and fast local dispersal. That is a vacuum. And people fill vacuums with stories. The most famous vacuum in maritime history is one of the very few where the evidence did not disappear at all, because the ship herself came back in perfect condition with everything still in her. On 7th November 1872, the brigantine Mary Celeste cleared New York for Genoa. She was 282 tons, a little under 31 meters, 12 years old, recently refitted. Her master was Benjamin Spooner Briggs, 37, a Massachusetts shipmaster from a seafaring family, a part owner of the vessel, described by everyone who dealt with him as careful and temperate. He had his wife Sarah aboard, and their 2-year-old daughter Sophia. Their 7-year-old son had been left at home for school. There were 7 crew. The cargo was 1,701 barrels of denatured alcohol, industrial grade, bound for Genoa, where it would be used in fortifying wine. Every element of that manifest matters. Alcohol is not oil or grain, it evaporates. Barrels of it in a sealed hold produce vapor, and alcohol vapor in the right concentration in air is flammable across a wide range and can be set off by a spark from almost anything. It also displaces oxygen. Loading it meant a hold you did not go into casually and hatches you thought about. And the barrels themselves were not uniform. Of the 1,701, most were white oak. Some were red oak. Red oak is more porous than white oak. The wood's cell structure allows liquid and vapor to pass in a way white oak's does not. When the cargo was eventually discharged at Genoa, 9 barrels were empty. Every one of the empty barrels was red oak. That is a fact from a cargo survey, not a theory. Something in that hold had been leaking. Briggs took the northern route across, and it was a bad passage, heavy weather. The kind that slows a small ship badly. The log kept going. The last entry is dated 25 November 1872 and puts her just off Santa Maria in the Azores, which after 18 days at sea was not good progress. On 5 December, the Canadian brigantine Dei Gratia, under Captain David Morehouse, Sargasso ad Workations, sighted a vessel about 400 nautical miles east of the Azores, yawing oddly and making poor course. Morehouse knew the ship. She had left New York 8 days before he did, and he knew Briggs personally. They watched her for 2 hours. Nobody appeared on deck. Nobody answered a hail. Morehouse sent his chief mate, Oliver DeVoe, with second mate John Wright and a seaman, across in a boat. What DeVoe found is the entire case, and it has been distorted so thoroughly in a century and a half of retelling that it is worth stripping back to what he testified to. The ship was deserted. Not damaged, not burned, not holed. Some sails were set, some were furled, some were gone or torn, and the rigging showed the kind of wear you would expect after heavy weather and days of nobody tending it. There was water in the hold, about a meter of it, roughly 3.5 feet, which sounds alarming and is not. That is a quantity a working pump could clear, and DeVoe pumped her out without difficulty. The vessel was sound. He and 2 men sailed her the several hundred miles to Gibraltar themselves. The fore hatch cover and 1 other hatch cover had been lifted off and were lying on the deck, not in place. The ship's single boat, a yawl that had been carried lashed over the main hatch, was gone. The rail where it had been was cut away or removed, consistent with the boat being launched rather than washed off. The chronometer, sextant, and ship's register were missing. Those are the 3 things a master takes when he leaves a ship intending to navigate. The cargo was intact and stowed. Provisions and fresh water for around 6 months were aboard. Personal possessions were largely untouched, including valuables. The galley gear was in place. The crew's oilskins and boots were still there. There was a sounding rod on deck. The sounding rod is the instrument you use to measure how much water is in the bilge. Somebody had been checking. All of that is the physical record. Everything else, in every version you have ever heard, is either interpretation or invention. There was no half-eaten meal on the table. There was no warm tea. There was no cat asleep on a locker. Those details were added later, mostly by a young Arthur Conan Doyle, who in 1884 published a short story about an abandoned ship he called the Marie Celeste, invented most of the famous imagery, and permanently contaminated the public memory of a real event. It is worth being specific about who was aboard, because the crew list is part of the evidence, and it has been slandered for a century and a half. Briggs was a part owner of the ship. That matters. A master with money in the hull does not abandon her casually, and he does not run her into trouble for someone else's insurance. He was known as a temperate man on a temperate ship. There was no alcohol served aboard as a matter of his own practice, which sits awkwardly against a century of retellings in which a drunken crew murders everybody. The 7 crew were mostly experienced and mostly foreign, which is entirely normal for an American merchant ship of the period. 2 of them, Volkert and Bas Lorenzen, were German brothers. Andrew Gilling was Danish. Their families were known, their reputations were checkable, and nothing about any of them supported the theory that was about to be built around them. The Lorenzens had written home shortly before sailing. Their letters are ordinary. Sarah Briggs had made ocean passages with her husband before. Sophia Matilda was 2 years old. There was a small organ aboard and a sewing machine. Both of them left where they were. The Dei Gratia's people brought her into Gibraltar on 13th of December and filed for salvage, which is the normal, legal, expected thing to do when you recover an abandoned vessel and her cargo at sea. Salvage law exists precisely to give crews a financial reason to take that risk. And then the case went sideways because of one man. Frederick Solly Flood was the Attorney General of Gibraltar and Advocate General for the Queen in her Office of Admiralty. He took one look at an intact, valuable, undamaged ship arriving under a salvage claim with her crew missing and concluded that he was looking at a crime. The hearings opened on 17 December 1872 and ran into March 1873. Solly Flood's theory shifted over time, but its core stayed the same. The crew had got at the alcohol, murdered Briggs and his family, and escaped, possibly in collusion with Morehouse for a share of the salvage. He hunted for physical proof and produced what he thought was proof. He reported marks on the deck he read as blood. He found a sword under the captain's bunk with staining on the blade. He pointed to cuts on the bow that he interpreted as deliberate damage designed to fake a wreck. Each piece failed under examination. The sword and the deck stains were analyzed by Dr. J. Patron, and the analysis did not support them being blood. The marks on the bow were consistent with ordinary weathering and the working of the timbers, rather than tool damage. The alcohol was denatured, which means it had been deliberately made undrinkable, and in any case the cargo hold of a laden brigantine is not a place a crew casually breaks into for a party. And the accusation against Morehouse never had a mechanism. He had left New York after Briggs. The 2 ships had not been in company, and the timing of the sighting does not support a conspiracy. The court could not find a crime. It also, notably, did not clear anyone in the way a modern verdict would. It simply awarded salvage, and the award tells you what the court really thought. Salvage of a sound ship and an intact, valuable cargo should have been substantial. The Mary Celeste and her cargo were valued at something in the region of $46,000. The award to the Dei Gratia's owners and crew was about $8,300, roughly a sixth. That is a court declining to accuse anybody while making very clear it was not comfortable. So what actually happened? The honest answer is that nobody knows, and nobody ever will, because 10 people got into a small boat and were never seen again. What can be done is to rank the reconstructions by how well they fit the physical evidence, and one of them fits considerably better than the rest. Start with the things that must be explained together. The ship was seaworthy. The boat was launched, not lost. The navigation instruments and the register went with the boat. The hatches were off. There was a sounding rod on deck. 9 red oak barrels of alcohol were empty on arrival, and there was no damage consistent with an event violent enough to force an evacuation. The reconstruction that carries most of that weight is a vapor scare. During or after the heavy weather, with the ship working, alcohol vapor escaping from the porous red oak barrels accumulates in the hold. Something makes it apparent. A smell, a noise, a rumble, as pressure equalizes. possibly a flash of flame with no lasting burn, which is a documented behavior of alcohol vapor ignition and can leave almost no scorching. Briggs, a careful master, with his wife and infant daughter aboard, is now faced with the possibility that he is standing on 1,700 barrels of explosive cargo. You open the hatches to vent. That explains the covers on deck. Then, you get everyone off the ship temporarily into the yawl, and you stand off at a distance and wait to see whether she blows up. You take your navigation instruments and your papers, because you never leave those. You do not take your oilskins because you expect to be back in an hour, and then you make one decision that has to be right. To avoid drifting away, you rig a tow line from the yawl to the ship, so that when the danger passes, you can pull yourselves back aboard. The tow line parts. That is the whole disaster. A brigantine with sails set, freed from the drag of a boat, in a returning breeze, seikis auiasimi imituri breeze, accelerates away from 10 people in an open yawl faster than they can row. There is no dramatic moment. There is a line going slack, and a ship gathering way, and a gap opening across water in the middle of the North Atlantic. They had a small boat, no chart of any use, whatever water they had grabbed, and hundreds of miles of open ocean. The Mary Celeste sailed on without them for 10 days. This matters well beyond one ship. Every element of the reconstruction is a reasonable decision. Venting a hold you suspect of accumulating flammable vapor is correct. Getting non-essential people, including a 2-year-old child, off a vessel you think might explode is correct. Keeping the ship attached to you by a line, rather than letting her drift free, is correct. The failure is a rope, and the killer is the wind coming back at the wrong moment. This is the signature of this ocean, and it is not supernatural in any respect. People end up separated from a perfectly sound vessel. Once separated, the distances involved make the outcome nearly certain, because there is nowhere to go, and almost nobody to see you. It has to be said clearly that this remains a reconstruction. The Gibraltar court reached no conclusion. No physical evidence of the yawl or of any of the 10 people was ever found. Competing explanations have been offered for a century and a half, including waterspouts, a seaquake, a faulty pump giving a false reading of water in the hold, and a panic caused by a misread sounding. Several of those are plausible in isolation. The vapor scare is the one that accounts for the largest number of the recovered facts simultaneously, and that is the strongest claim anyone is entitled to make. What happened afterwards is almost more revealing than the case itself. The Mary Celeste was returned to her owners, sold repeatedly, gained a reputation as unlucky, and was finally run deliberately onto a reef off Haiti in 1885 in a crude insurance fraud that collapsed when surveyors examined the worthless cargo. The ship died in an ordinary swindle. The story, though, kept growing, and it grew in a specific direction. Every retelling added detail that made the abandonment less explicable and the ocean more sinister. By the 20th century, the Mary Celeste had become the standard example of something inexplicable happening in the Western Atlantic, and it was doing a job. It stood in for a mechanism nobody could see. The real lesson, that a sound ship and a separated crew are two different objects with two different fates, was far less entertaining than a ghost. And that mechanism was about to take something very much larger than a brigantine, in an ocean crossed by radio, in wartime, with 309 people aboard. The USS Cyclops was not a small ship, and she was not a mystery ship. She was a Proteus-class fleet collier, launched in 1910 at Cramps Yard in Philadelphia, 542 feet long, 65 feet in the beam, built to carry coal to the fleet and fitted with a forest of coaling booms down her center line. In the spring of 1917, the United States entered the war, and Cyclops was commissioned into the Navy proper. She spent the following months hauling coal across the Atlantic and down to South America. which is exactly the unglamorous work that decides wars. Her commanding officer was Lieutenant Commander George W. Worley, and Worley is a complicated presence in this story. He had been born Johann Friedrich Wichmann in Hanover in 1862, jumped ship in San Francisco at 16, run a saloon on the Barbary Coast, and worked his way up through merchant command before joining the Naval Auxiliary Reserve in February 1917. He was, by multiple accounts from his own crew, a harsh and erratic officer. There were complaints of brutality. There were stories of him conducting rounds in his underwear and a derby hat, and of chasing an ensign around the deck with a pistol. There was, in a navy at war with Germany, persistent suspicion about a German-born captain, and none of it was ever substantiated as anything more than what it was: a difficult man running a hard ship. In January 1918, Cyclops went south to Brazil. The objective was straightforward and had nothing to do with coal. Britain and the United States needed manganese because manganese goes into steel. And steel was the war. She loaded at Rio de Janeiro and sailed on 16th of February, called at Salvador on the 20th, and set course north for Baltimore. Now the conditions of apparent control start coming apart, one at a time, and every step is documented. The first is the cargo. Cyclops was designed to carry 8,000 long tons in normal service. She was loaded with 10,800 long tons of manganese ore. That is not simply too much weight. And this is the single most important technical point in the whole loss. Coal and ore are completely different cargoes to a naval architect. Coal is light and bulky. Fill a collier's holds with coal, and the weight distributes itself through the full volume of the ship fairly evenly, fairly high. Manganese ore is dense. It is heavy rock. To carry 10,000 tons of it, you fill only the bottom of each hold and leave the upper volume empty, which concentrates enormous mass low down and in the middle of the hull, with voids above it. Two things follow. A ship loaded that way becomes extremely stiff. Her righting moment is powerful, so instead of rolling gently, she snaps back upright hard and fast, which puts violent, repeated shock loads through the structure. And the hull girder itself, the whole ship considered as a single long beam, is now carrying its heaviest load in a way it was never designed for. Ore also shifts. Unlike coal, which packs, a dense granular cargo in a partly filled hold can slide bodily to one side when the ship rolls in a seaway, and once it has slid, it does not slide back. The second problem is the engine. Cyclops had two triple expansion steam engines. Before or during the voyage, the starboard engine developed a cracked cylinder, and it was reported as condemned and inoperative. She was going to make the passage north on one engine at reduced speed. Think about what that removes. A ship with one engine cannot maneuver freely, cannot hold a course as easily in a heavy quartering sea, and cannot outrun weather. She is committed to whatever the ocean gives her for longer. The third problem showed up at Barbados. Cyclops made an unscheduled stop there in early March, which she was not supposed to do, and the reason recorded was that she was riding too deep. Her plimsoll line, the load mark that says how much of a ship must remain above water, was under the surface. At Bridgetown, she took on more coal and provisions. The American consul at Barbados, Brockholst Livingston, reported afterwards on what he had seen and heard, including the overloading and the state of the ship, and his report is one of the reasons the loading question was taken seriously later. Nobody stopped her. There was a war on, the manganese was needed, and the alternative to sailing was leaving thousands of tons of strategic ore sitting in the Caribbean. She left Barbados on 4th of March 1918 with somewhere around 309 people aboard, her own officers and crew, plus passengers. Among them was Alfred Louis Moreau Gottschalk, the United States Consul General at Rio de Janeiro, going home. There were also naval detainees being transported and assorted personnel taking passage north. She was due in Baltimore on 13th March. She never arrived. And here is where this loss separates itself from everything before it. This was 1918, not 1872. Cyclops had radio. She was in a naval communications system with shore stations and a war-footing reporting structure. She was steaming a well-traveled route in a period of heavy traffic. If a ship of that size was in trouble and had any time at all, the expected behavior was a transmission. There was no distress signal. Nothing was received from her after she cleared Barbados. The search was enormous by the standards of the day and completely fruitless. Ships were diverted. Coastlines and islands were checked. Inquiries went to every port she might conceivably have limped into. Nothing was found. No boat, no body, no oar, no life ring, no oil, no wreckage of any kind, then or since. In the more than a century that has followed, with side-scan sonar, with the deep-water search technology that found the Titanic and the Bismarck, the Cyclops has never been located. It is worth pausing on how a search like that was conducted in 1918 because the limits are the point. There was no radar and no aerial search worth the name. Finding a missing ship meant sending other ships to look, along her expected track and to either side of it, with lookouts using their eyes. A vessel steaming a search pattern at 12 knots with a horizon of perhaps 10 miles either side covers a strip of ocean that sounds enormous and is, against the area involved, close to nothing. Wartime made it worse. Escort and convoy work had first call on every hull. The Atlantic was full of traffic under orders to run dark and maintain radio discipline, and the assumption for weeks was that Cyclops might simply have gone silent and put into a port somewhere. Several hundred families were being told nothing, because there was nothing to tell them. The Navy's notifications went out in stages as the possibility of a delay collapsed into the certainty of a loss. 309 people is the largest loss of life in United States Navy history, not involving combat. The official position has never changed and has the merit of being honest. The Navy's own historical summary states that the disappearance of the ship has been one of the most baffling mysteries in its annals, and that every attempt to locate her proved unsuccessful. Cause undetermined. Because there was no wreck and no witness, the theories multiplied immediately, and they have never stopped. German submarine or mine, which is the obvious wartime guess, and which the German naval records examined after the war do not support. No U-boat claimed her, and there were none operating in that area at that time. Mutiny, on the strength of Worley's reputation. Sabotage, on the strength of his birthplace. Treachery by Gottschalk. Sea monsters later. A hole in the ocean, later still. The engineering answer arrived slowly from people who understood what was actually in her holds. Rear Admiral George Van Deurs, who had studied the ship, argued that the longitudinal I-beams running the length of Cyclops had been corroded by the cargo she habitually carried, weakening exactly the structural members that hold a long hull rigid. Put a weakened hull girder into a seaway of 30 to 40 knots of wind, where a 540-foot ship regularly finds herself supported at the bow and the stern by two wave crests with a trough amidships, and the unsupported middle takes a bending load it was never designed to take, made worse by 10,000 tons of dense ore concentrated precisely there. A hull girder that fails does not sink like a ship in a film. It breaks. A vessel loaded with ore that breaks amidships goes down in a very small number of minutes, sometimes less than one, and it goes down at both ends at once as the two halves fill. There is no time to launch a boat. There is no time to send a signal. And what floats away afterwards from a steel ship carrying rock is close to nothing. For a long time that remained an argument. Then the ocean ran the experiment again, twice in the same year. Cyclops had sister ships. Proteus and Nereus were the same class, built to the same drawings, and by 1941 both had been sold out of naval service and were working commercially. Proteus went to the Canadian Merchant Navy. Nereus was sold to the Aluminium Company of Canada in February 1941 and put on the run from the Caribbean to North American smelters. Both of them were now carrying bauxite. Bauxite is aluminium ore. It is dense rock. It is, in every way that matters to a hull, the same kind of cargo as manganese ore. Proteus was lost without a trace somewhere in or near the Caribbean after 25 November 1941, with 58 people aboard. Nereus was lost without a trace after departing St. Thomas in the United States Virgin Islands, sometime after 10th of December 1941. Neither wreck has been found. Neither loss produced meaningful debris. 3 ships of one class, all carrying heavy metallic ore, all vanishing without a trace, across 23 years. And that should permanently change how you read every disappearance in this ocean. The common factor is not a location on a chart. It is a design, a cargo, and an aging structure. The Atlantic did not select these ships because of where they were. They failed because of what they were and what was in them. And the ocean's only contribution was to be deep enough and large enough to erase the evidence, which is the property this ocean has had all along. A fast total loss out here produces nothing recoverable. That is not an anomaly requiring an exotic explanation. It is the default outcome, and it is the raw material out of which a myth was built. 2 more losses did most of the rest of the work, and both of them have been examined more carefully than almost any accident in maritime or aviation history. On the afternoon of 5th December 1945, 5 TBM Avenger torpedo bombers took off from Naval Air Station Fort Lauderdale on a routine navigation training exercise. The plan was a triangular course out over the Bahamas, east to a practice bombing area, north, then southwest back to base. The exercise was so ordinary it had a name and a number, and the number was Flight 19. The flight leader was Lieutenant Charles Taylor, an experienced naval aviator with somewhere around 2,500 flying hours and combat tours in the Pacific behind him. Behind him in the other aircraft were students and crewmen, 14 men in total. The initial condition was control, good aircraft, a competent leader, a familiar exercise, decent weather at takeoff. The first warning came by radio, and it is the reason this case is documented at all. Other stations could hear them. Taylor reported that his compasses were not working. He believed he was over the Florida Keys, which meant that in his mind, the Gulf of Mexico lay to the west, and Florida lay to the east, so the way home was to fly east and northeast. He was not over the Keys. He was well to the north, over the open Atlantic east of Florida. Flying east from there does not take you to Florida. It takes you into 3,000 kilometers of ocean. This is worth being precise about, because it is one of the very few disasters where you can watch the exact moment a correct procedure applied to a wrong premise becomes fatal. Taylor's reasoning was internally sound. If you are over the Keys with dead compasses, heading east is the right call. Every subsequent decision he made followed logically from a starting position that was wrong by a couple of 100 miles. The practical pressures made it worse. The weather deteriorated through the afternoon, the sea state built, and the light went. Radio conditions were poor and getting poorer, with interference from Cuban commercial stations bleeding across the training frequencies. Ground stations, trying to help, could hear fragments. Attempts to get the flight to switch to an emergency frequency that would have allowed direct fixing were resisted, reportedly because Taylor did not want to lose contact with the other aircraft in his formation, which is again a defensible instinct that closed a door. Options disappeared one at a time. Daylight went. The weather closed. The formation flew east, then west, then east again as the debate over position continued, burning fuel on every leg. The last transmissions heard suggested the aircraft were preparing to ditch together when the first of them ran dry. A TBM Avenger ditching at night in a heavy sea is not a survivable proposition for most crews. The aircraft is heavy, it goes down fast, and finding rubber life rafts in the dark in open ocean in 1945 was close to hopeless. Now the second half, and this is the part that changes what the incident means. The Navy launched a search while the flight was still in the air. Among the aircraft sent out was a Martin PBM Mariner flying boat, Training 49, out of Naval Air Station Banana River, with 13 men aboard. It took off at around 7:20 in the evening. It transmitted a routine message shortly afterwards. Then, nothing. At about the same time and in the same area, the merchant tanker SS Gaines Mills reported seeing a burst of flame in the sky, an explosion, and burning fuel on the water. The ship went to the position and searched. She found a slick in debris and heavy seas and recovered nobody. The PBM Mariner had a reputation among the men who flew it. It carried enormous quantities of fuel. Its interior tended to accumulate fumes, and crews referred to it as a flying gas tank. Explosions in that type were a known problem. So the loss of Flight 19 is one accident. The loss of the Mariner is a second, separate accident, and it happened because the aircraft was launched into bad weather at night to look for the first one. 27 men died that evening, 14 in the training flight, 13 in the aircraft sent to save them. The Navy's Board of Inquiry examined it thoroughly. The original finding attributed the loss of Flight 19 to Taylor's navigational error, which his mother later contested. The record was subsequently amended to cause unknown, which is where it remains. What was never in dispute was the sequence. Compasses reported as failed, a leader convinced he was somewhere he was not, a flight heading away from land, deteriorating weather, darkness, and fuel exhaustion. No wreckage from any of the 5 Avengers has ever been positively identified. Aircraft have been found off the Florida coast over the decades and examined and ruled out. Something is buried inside the most famous case in the whole legend, and it is not what the books sell. It is not that 6 aircraft vanished inexplicably. It is that the rescue was itself a dangerous operation, conducted at night into a building sea, and it killed nearly as many people as the original emergency. That is a rule with no exceptions anywhere in this story, from a flying boat lifting off into the dark over the Bahamas in 1945 to a Coast Guard crew that would one day fly a 4-engine turboprop into the middle of a hurricane. Somebody has to go out into the same conditions that created the emergency. There is no version where help arrives from outside the weather. The second case is from 1963, and it is the exact opposite of a vanishing. The SS Marine Sulphur Queen was a T-2 tanker, built in 1944 as an oil carrier, and in 1960 she was heavily converted to carry a cargo almost nobody else carried: molten sulfur, held liquid at around 120 degrees Celsius in an insulated tank system, kept hot by steam coils, for the whole voyage. The conversion is the story. To create one enormous cargo tank capable of holding molten sulfur, most of the transverse bulkheads inside the original tanker were removed and replaced with a different internal support arrangement. Transverse bulkheads are not partitions. They are structural members that stiffen a hull against twisting and bending. Taking them out to make room for a specialized cargo weakens the ship as a beam, in the same fundamental way that corroded longitudinal members weakened Cyclops. She sailed from Beaumont, Texas, on 2nd of February 1963 with 15,260 tons of molten sulfur and 39 crew, bound for Norfolk, Virginia. On 4th of February, she sent a routine position report from the Gulf of Mexico, roughly 200 miles west of the Florida Keys. That was the last message. No distress call. The search ran for 19 days, and this time, the ocean gave things back. On 20th of February, a United States Navy vessel recovered a stenciled life preserver and a foghorn cone about 12 nautical miles southwest of Key West. More debris followed: life jackets, a name board, a shirt, fragments identifiable as hers. Debris but no bodies, and no hull. The wreck has never been positively located. The Coast Guard's Marine Board of Investigation went through the ship's history in detail and produced a finding that is far more damning than any mystery. It concluded that the vessel was in an unsafe and unseaworthy condition and should not have sailed. Her tank system had a history of leaks and fires. Her structure had been compromised by the conversion. The board set out several possible sequences by which she could have been lost, including an explosion of sulfur vapor, a capsize, or the hull breaking in two, and it declined to rank them, because without the wreck, it could not. 2 losses, 18 years apart, both filed under the same legend. One produced no wreckage at all, and the other produced identifiable debris within a fortnight. One was an aircraft navigation failure compounded by weather and darkness. The other was a ship that a formal investigation said should never have left the dock. Neither of them needs an unexplained force. Both of them needed an ocean big enough and deep enough to prevent anyone from proving what happened. And this ocean is very good at that. The building took about 25 years, and it can be traced almost entry by entry. In 1950, a journalist named Edward Van Winkle Jones wrote a short piece for the Associated Press about a cluster of ships and aircraft lost between Florida, Bermuda, and Puerto Rico. In 1952, a magazine article by George X. Sand described the same idea as a triangle of unexplained disappearances. In 1964, a writer named Vincent Gaddis published an article in a pulp magazine titled The Deadly Bermuda Triangle, and that phrase is the moment the thing acquired a name and a shape. Gaddis expanded it into a book the following year. Others followed. In 1974, Charles Berlitz published The Bermuda Triangle, which sold in the millions and pushed the concept into global culture, complete with lost continents and unknown energies. The method in these books is consistent, and once you see it, you cannot unsee it. Take a real loss, remove the weather, remove the mechanical condition of the vessel, remove the cargo, remove the distance from help, present what remains, which is a ship that went out and did not come back, and call it inexplicable. In 1975, a research librarian at Arizona State University named Lawrence David Kusha did the obvious thing that nobody had done, which was to go and check. Kusha worked case by case. He went to Lloyd's of London. He went to the United States Coast Guard. He went to the Air Force, to newspaper archives from the actual dates, to inquiry transcripts, to the original accident reports. And what he found repeatedly was that the published accounts had been wrong in ways that were not random. Ships described as vanishing in calm seas turned out to have been lost in documented storms, sometimes hurricanes, which were reported in the newspapers at the time and simply omitted from the books. Vessels described as disappearing inside the triangle turned out to have been lost hundreds or thousands of miles outside it, in one case in the Pacific. Some incidents had been reported as unsolved when the wreckage had been found and the cause established. At least one vessel had never existed in the form described. Kusha's conclusion, published as The Bermuda Triangle Mystery Solved, was blunt. The legend was a manufactured mystery, assembled through careless research, repetition of earlier errors, and in some cases deliberate sensationalism, and it had grown because each writer copied the previous writer instead of the source documents. The institutional record supports him. Lloyd's of London, which has more financial incentive than anyone alive to know precisely where ships are lost, has found no statistically elevated loss rate in that region. Insurance rates for the area are not higher than for comparable ocean areas. The United States Coast Guard's position is the same. It does not recognize the Bermuda Triangle as a geographically distinct hazard, and its records do not show an anomalous concentration of unexplained losses. And this is the finding most people find deflating, right up until they think about what it actually implies. This region is not statistically special. It is dangerous for reasons that are entirely mundane and completely sufficient. It is one of the most heavily trafficked ocean areas on Earth. It is enormous. It sits directly under the recurving track of Atlantic hurricanes. And for most of its history, It was crossed by vessels whose position was an estimate. Put actual numbers against that. The waters between Florida, the Bahamas, Bermuda, and the Caribbean carry an extraordinary density of movement. Container and bulk traffic in and out of the eastern United States and the Gulf, the entire cruise industry, tankers, fishing vessels, hundreds of thousands of private craft operating out of Florida alone, and a volume of general aviation and airline traffic crossing the same boxes on the chart. Every one of those is a chance for something to go wrong. And the region includes the Straits of Florida, the Bahama Banks with their sudden shallows, the Gulf Stream's western wall, and a hurricane season that runs from June into November. Take a lot of ships, put them in a big area, run tropical cyclones across it every summer and autumn, and you will lose some. The losses cluster where the ships are, because that is what losses do. Deflating the myth does not make the water safer. It moves the danger from the supernatural column into the operational column, where it has always been and where it still is, which raises the question that the myth's collapse leaves standing. If there is nothing anomalous here, and the mystery was a publishing phenomenon, then why does this particular stretch of ocean keep producing situations where modern, well-equipped, well-informed people run out of options? The answer is that nothing in the physical system has changed. And the best modern demonstration of that involves a ship that everybody could see coming, on a night when the entire United States was watching the weather. First, the piece of water she died on, because it is the last mechanism in this system, and it is the most violent one. The western boundary of the Sargasso Sea is the Gulf Stream. That is not a metaphorical border. It is a river of warm water 50 to 100 kilometers wide, running northeast along the American continental margin at speeds that can exceed 4 knots, carrying more water than every river on Earth combined. Its edge, where the warm, fast core meets the colder, slower shelf water inshore of it, is called the Western Wall. And on a satellite temperature image, it shows up as a line so sharp it looks drawn. What happens at that line is simple physics with brutal consequences. Waves are generated by wind, and they travel with a certain length between crests. Push those waves into a current running the opposite way, and the current compresses them. The wavelength shortens, the wave height increases, and the face of the wave steepens. Same energy, worse shape, so when a cold front or a tropical system drives wind out of the north or northeast, and that wind opposes a Gulf Stream running hard to the northeast, the sea state in that narrow band becomes disproportionately dangerous. Not just big, short and steep and close together, which is a different problem for a vessel. A long swell you ride, a short steep sea hits you before you have recovered from the last one, so the bow is still driving down when the next crest arrives, and the ship stops rising and starts going through instead of over. Water comes aboard. The vessel loses way. Every impact is transmitted straight into the structure. Sailors have known about this piece of water for centuries under a different name. The stretch of coast just inshore of it, around Cape Hatteras, is called the Graveyard of the Atlantic, and the count of wrecks along those shoals runs into the thousands. Hatteras is where the Gulf Stream turns away from the coast, where the cold Labrador water meets it, where Diamond Shoals reaches out from the Cape into the shipping lane, and where two weather regimes collide often enough that the National Weather Service treats it as its own problem. On 25th October 2012, a wooden tall ship left New London, Connecticut, and headed for that piece of ocean on purpose. The Bounty was 108 feet of ship built in Nova Scotia in 1960 for the MGM film Mutiny on the Bounty, an enlarged replica of an 18th century Royal Navy vessel, built in wood by traditional methods, to a design that was already antique when the original was launched. After the film, she had spent half a century as an attraction, a sail training vessel, a film ship again, and a floating piece of promotion, sailing between ports where people paid to come aboard. She was operated as a moored attraction vessel which is a legal category with far lighter inspection requirements than a passenger ship. She was 52 years old, and she was tired. That is not hindsight. It was known. She needed yard work on her hull, and the plan was to reach Florida, where the money and the facilities were, and haul her out. Her captain was Robin Walbridge, 63, who had commanded her for 17 years. He knew that ship better than anyone alive. He had a documented view about weather, and he had expressed it publicly more than once, that a ship is safer at sea than tied to a dock in a storm, because in port she can be pounded against a pier or thrown ashore, and at sea she has room to maneuver. That is not a crank opinion. It is a genuinely orthodox piece of seamanship, and it has kept a lot of vessels alive. There were 16 people aboard, several of them young, several with limited deep water experience. Crew members raised concerns about the trip before departure. Walbridge, by the accounts given afterwards, told the crew that anyone who did not want to sail could stay behind, and nobody left. The initial condition of apparent control was information. This is what makes the Bounty case so much harder to look away from than anything else in this story. Hurricane Sandy was not a surprise. It was one of the most heavily forecast storms in American history. Days out, the models had it, the National Hurricane Center had it, and the projected track and the projected size were on every screen in the country. Walbridge had access to all of it. He looked at a well-forecast hurricane and formed a plan around it. Run southeast. Get out to the east of the storm's track, let it pass to the west, then turn and run down to Florida behind it. Ships do that. It is a recognized strategy. It depends entirely on the storm behaving as forecast and on your vessel being able to make the speed you assumed. Sandy did not behave like a normal hurricane, and the ways in which it did not are exactly the ways that closed the escape route. It was extraordinarily large. Its tropical storm force wind field spanned well over 1,000 miles at its greatest extent, which meant that getting east of it required a far bigger offset than the track line suggested. And instead of recurving out to sea in the usual way, Sandy turned left toward the American coast, driven by an unusual blocking pattern to the north. A vessel that had positioned itself east and south of the projected track found the storm coming toward it. The first concrete warning aboard was water. Bounty always leaked. Wooden ships do, and the crew were used to running pumps as routine housekeeping. On 28 October, the amount stopped being routine. The water in the bilges was gaining faster than expected, and the crew were tracking it. The interpretation was reasonable at first. More motion means more working of the seams, which means more water, and you pump it out. The practical pressure was that there was no longer any good alternative. Turning around meant crossing back through the storm's path, and running for a port meant closing a coast in a hurricane, which is the classic way to lose a ship. Then they began losing options in sequence. The dewatering system depended on the generators, and the generators depended on the engine room staying dry enough for the electrics. As water rose, that relationship inverted. They needed the pumps to protect the machinery that ran the pumps. The main engines were also affected. The vessel's ability to hold a heading, which she needed to take the seas on the right part of her hull, degraded. At some point the hydraulic pumps and then the main engines went, and Bounty was a wooden sailing ship without power in a hurricane. They tried to regain control. They rigged what they could. They moved water by hand where possible. They kept people working. The NTSB later noted that the crew fought the flooding for a long time with the equipment they had. This is not a story about people giving up. The second complication was the state of the ship herself. The investigation afterwards found significant rot in the vessel's timbers and problems with recent caulking work. A wooden hull with soft frames and poorly caulked seams in a short, steep sea does not fail all at once. It works, and the working opens more seams, and the leak rate is not constant but accelerating. Every hour of pounding made the following hour worse. At 20:45 on 28th October, the ship's organization ashore relayed the situation to the United States Coast Guard, Sector North Carolina. Now watch the rescue, because a rescue is not a helicopter arriving. It is a chain of decisions and physical constraints, and each link takes real time. Recognition came first. Sector North Carolina had a report of a vessel in distress roughly 100 miles offshore, in the middle of a hurricane, at night. The exact distance is reported variously between about 90 and 130 nautical miles southeast of Cape Hatteras, depending on which position and which moment you use. And that spread itself tells you something about how uncertain the picture was. Authorization and asset selection came next, and it was constrained. A helicopter has a fixed amount of fuel and therefore a fixed radius of action, and that radius shrinks when you have to fight a headwind out and hold a hover on scene. Sending helicopters into a hurricane at night, at that distance, to search for a vessel whose exact position was uncertain, was not a survivable plan. So the Coast Guard did the correct thing and sent an aircraft that could stay. An HC-130 Hercules launched from Air Station Elizabeth City, North Carolina, into winds already in excess of 60 knots and flew out to the position. Its job was not to rescue anyone. A fixed-wing aircraft cannot hoist. Its job was to find the ship, establish communications, and hold overhead through the night, so that when helicopters could be launched, there was something to send them to. That aircraft orbited above Bounty for hours in the dark, in a hurricane. It talked to the crew by radio. It dropped flares. It dropped additional life rafts. It dropped a self-locating data marker buoy, which is a device that floats and transmits its own position, so that searchers could measure how the water was actually drifting rather than guessing. At 04:45, the ship's chief mate, John Svensson, radioed the Hercules that Bounty was sinking and the crew needed immediate help. Before they could conduct an orderly abandonment, the ship went over. A knockdown in that sea rolled her onto her side, and people who had been on deck in survival suits, clipped on or holding on, went into the water among rigging and spars and rolling masts. That is the worst possible way to leave a ship. Not a controlled entry into a raft, but a scatter of people in the dark, in 30-foot seas, with 108 feet of wooden hull and its rig moving unpredictably among them. Some got into life rafts, some did not at first, and had to swim to them. The crew had been in survival suits for hours by then, which is the right call and has its own costs. An immersion suit keeps you alive in the water and makes you clumsy on a moving deck, hot and hard to work in. People had been climbing over a wooden ship rolling heavily in a hurricane, in bulky suits, in the dark for most of the night, while the water inside her rose. They were also trying to do the one thing that a tall ship makes genuinely difficult. Abandoning a modern vessel means launching rafts clear of the hull and getting into them. Abandoning a square rigger means getting past a rig. Masts, yards, standing rigging and running rigging, all of it in the water once she goes over. All of it moving with the swell. A life raft alongside a rolling wooden hull with spars in the water is not a refuge. It is a hazard. The helicopters launched. 2 MH-60 Jayhawks from Elizabeth City, the first commanded by Lieutenant Commander Steve Cerveny, the second by Lieutenant Commander Steve Bond. They arrived on scene just after first light at around 06:30. By the time they got there, Bounty was effectively gone, with masts visible in the water. Picture what a hoist looks like in that environment. The aircraft has to hold a hover over a target that is rising and falling perhaps 30 feet with every wave, in wind that is gusting hard and shifting direction, while a rescue swimmer goes down on a cable. Petty Officer Second Class Randy Haba went into that water to work the first raft. Petty Officer Third Class Dan Todd went in for the second. Waves were breaking over the tops of the life rafts. Each survivor has to be reached, secured, and brought up individually, and the aircraft cannot simply stay. Every minute of hovering burns fuel it needs to get home, at a distance that is already near the practical limit. The first Jayhawk hoisted 5 people. The second hoisted 9. 14 survivors were flown back to Elizabeth City. 2 people were unaccounted for. Claudine Christian, 42, was located later, roughly 7 nautical miles from the vessel's reported position, unresponsive. She was recovered and flown to hospital, where she was pronounced dead. That distance is worth holding on to. 7 miles of drift in a matter of hours from the place the ship went down. That is what the sea state and the current do to a person in the water. And it is why searching for a human head in the open Atlantic is close to impossible without a beacon. Robin Walbridge was never found. The Coast Guard searched for more than 90 hours across roughly 12,000 overlapping square nautical miles before suspending the case. The National Transportation Safety Board's finding was unusually direct for that organization. The probable cause of the sinking was the captain's reckless decision to sail the vessel into the well-forecast path of Hurricane Sandy, which subjected an aging wooden vessel with an inexperienced crew to conditions from which the vessel could not recover. Contributing factors included the ship's deteriorated condition, including rot in her timbers and inadequate caulking, and inoperative dewatering equipment. Now, the uncomfortable part, and the reason this incident belongs at the end of the chain rather than as an isolated tragedy. Every single piece of modern technology in this story worked exactly as designed. The forecast was correct, and it was available days in advance with a precision that would have been science fiction in 1918. The satellite communications worked. The distress reached the Coast Guard within minutes of the decision to send it. The search and rescue organization functioned. Recognition, launch, on-scene presence within hours, aircraft holding station all night, helicopters at first light, 14 people lifted out of a hurricane and delivered to a hospital. That is an extraordinary performance. And none of it moved the ship. None of it reduced the distance. None of it made a 52-year-old wooden hull stop taking water, or put the generators back online, or made the sea smaller. What technology changed was the range of things people were willing to attempt. A hurricane you cannot see is a hurricane you avoid by being nowhere near that ocean in October. A hurricane you can see, modeled, with a projected track on a screen, becomes a thing you can plan around. The forecast did not cause the decision to sail, but it made the decision look calculable. The presence of a rescue service that genuinely can pull people out of a hurricane at 100 miles offshore does the same thing at a deeper level. It quietly shifts where the edge of acceptable risk sits, for everyone, all the time. And that is the trade-off. It is not an argument against forecasting or against the Coast Guard. It is an observation about how capability gets spent. Improvements in safety are rarely banked as safety. They are usually banked as reach, and the reach has a hard limit, which is the last thing the bounty proves and the thing that closes this loop. Those helicopters could reach her. Elizabeth City, to a position roughly 100 miles southeast of Hatteras, is inside an MH-60's operating radius, with fuel to hover and hoist and return. The C-130 could get there fast and stay for hours. That is why 14 people are alive. Move the same accident 500 miles further out into the Sargasso, into the middle of the gyre where the calm is, and the entire chain breaks at the same link every time. The signal still gets through because satellites do not care about distance. The recognition is instant, the authorization is immediate, and then somebody has to draw a circle on a chart, and the position is outside it. Bermuda is the only place inside this sea from which anything can be launched, and Bermuda cannot launch much. For 14 years it could. The United States Coast Guard commissioned an air station on the island on 31st October 1952, initially to support Navy operations and increasingly to cover civil aviation crossing the Atlantic. It flew PBM-5A flying boats, then Martin P-5M Marlins, then Grumman HU-16 Albatrosses, and its aircraft were repeatedly scrambled for aircraft that had lost an engine over open water halfway between continents. A rescue coordination center ran alongside it. It was decommissioned in 1966. The reason was not cost-cutting for its own sake. It was that commercial aircraft had become reliable. Piston engines gave way to turbines, four-engine airliners stopped dropping into the ocean at the rate that had justified a mid-Atlantic rescue base, and the requirement evaporated. That is a genuine safety success. It also removed the only permanent long-range rescue capability inside the Sargasso Sea, and it has never been replaced. What exists now is a coordination function. The Bermuda Maritime Operations Center runs the island's rescue coordination, works around the clock, and covers an area of ocean vastly larger than anything it can physically reach. In practice, its own resources handle incidents effectively out to roughly 30 miles from the island. Beyond that, it does the only thing available. It coordinates. It talks to the United States Coast Guard, to Caribbean and European authorities, and it looks for ships. The actual mid-ocean rescue system is nothing like what people imagine, and the reason matters. The primary asset in the middle of the Atlantic is not an aircraft. It is a merchant vessel that happens to be somewhere nearby. Since 1958, the Coast Guard has run a voluntary global reporting system called AMVER. Merchant ships on offshore voyages send in a departure report, then position updates at least every couple of days, then an arrival report. The system builds a continuously updated picture of where the world's shipping actually is. When a distress comes in from the middle of an ocean, a rescue coordinator queries AMVER, sees which participating vessels are within reach, and asks a master to divert. It works. It has saved thousands of people. It is also governed by arithmetic that nobody can argue with. A large merchant ship makes perhaps 14 to 18 knots in good conditions, and considerably less when she is punching into a heavy sea. If the nearest AMVER vessel is 200 nautical miles away, that is somewhere between 12 and 18 hours before she is on scene, and she has to find you when she arrives, from a bridge maybe 30 meters above the water, looking for an object the size of a life raft in a running sea. If the nearest ship is 400 miles away, you are talking about a day and a half. Long-range aircraft can compress the search phase enormously, and they do. A C-130 can be overhead in the middle of the Atlantic in a few hours, find you, drop equipment, and stay. What no aircraft can do is take you out of the water. Hoisting requires a helicopter, and a helicopter's useful operating radius, with fuel to search, hold a hover, and return, is a few hundred miles, not 1,000. Coast Guard helicopters have flown to Bermuda, refueled there, and continued outbound to reach casualties, which extends the reach but adds hours and depends on the geometry being kind. So the rescue picture in this sea has a specific shape. Near Hatteras, near Florida, near the Bahamas, within a few hundred miles of the coast, the response is fast and capable and repeatedly proven. Move into the middle, into the calm, into the part of the ocean where the weed is and the wind is not, and the helicopters cannot come. What comes is a merchant ship, hours or a day later, if there is one. There is one factor in the Sargasso that genuinely runs in a casualty's favor, and it is worth being fair about it because almost nothing else here is. The water is warm. Surface temperatures across most of this region sit somewhere in the low to mid-20s Celsius through much of the year, and in summer higher. In the North Atlantic off Newfoundland or in the Norwegian Sea, immersion is a clock measured in tens of minutes. Cold shock hits in the first minute or two. Involuntary gasping fills airways. Grip strength goes within about 10 minutes as the hands cool, and useful consciousness follows. In water in the 20s, none of that applies in the same way. A person in a life jacket in the Sargasso can survive for many hours, and with a raft, considerably longer. So the sea that starves you of wind and food will not, in most conditions, kill you quickly by temperature. That is a real advantage, and it has kept people alive. it changes nothing about being found. A human head in the water is roughly the size of a grapefruit, showing perhaps 15 centimeters above the surface, in a swell that is rarely completely flat. From the bridge of a merchant ship, from 30 meters up, in good light and calm conditions, a searcher might see that at a mile or two. In any sea state at all, far less. An aircraft flying a search pattern at a few hundred feet covers ground fast and sees very little of it in detail. This is why every serious offshore safety system is built around beacons rather than eyesight. An emergency position indicating radio beacon or a personal locator beacon on a life jacket turns an impossible visual search into a coordinate. Without one, warm water simply extends the period during which a person is alive and unfound. That is the honest shape of survivability out here. The temperature buys you time. The geography spends it. And here is the geometric cruelty of the thing. The center of the gyre is the emptiest part of the ocean surface in every sense. No wind, no nutrients, no fish, no coastline, and the thinnest shipping traffic, because commercial routes follow great circles between real ports, and there are no ports out there. The place where you are most likely to be delayed is also the place where you are least likely to be found. It is the modern version of the same equation that killed people in the horse latitudes. It is no longer casks of water divided by days of calm. It is hours of survival divided by distance to the nearest hull. The units changed. The structure did not. Which makes it genuinely strange that this same emptiness turns out to be one of the most important pieces of biological real estate on the planet, and that we still cannot watch the thing that happens there. In 1904, a Danish researcher named Johannes Schmidt was aboard a vessel off the Faroe Islands, working on food fish, when the crew brought up a small transparent creature shaped like a willow leaf. It was a leptocephalus, the larval form of an eel, and at the time nobody knew where European eels came from. That sounds like a small gap in knowledge. It was enormous. Eels were a major European food source and had been for millennia. They appear in rivers as tiny transparent glass eels, live for years or decades in fresh water, grow, and then one autumn they change. Their eyes enlarge, their bodies silver, their digestive systems begin to shut down, and they leave, heading downriver to the sea. Nobody had ever found an eel egg. Nobody had ever found a spawning adult. Aristotle concluded eels arose spontaneously from mud. Later naturalists proposed everything from horsehair to beetles. Schmidt decided to solve it by geometry, and the method is beautiful in its simplicity. If you catch larvae across a large area and measure them, and if larvae grow as they drift away from where they were born, then the smallest larvae must be nearest to the source. Map the sizes. Follow the gradient down. The point where the smallest ones are is the spawning ground. Executing that took 18 years. He towed nets from research vessels, and when research vessels were not available, he persuaded merchant captains to tow for him, distributing gear and instructions to ships crossing the Atlantic on ordinary commercial voyages. The First World War interrupted everything and made large stretches of ocean impossible to work. Ships were lost. One of his own vessels, the Margareta, was wrecked in the Caribbean. He kept going, year after year, across the Atlantic and the Mediterranean, accumulating tens of thousands of measured larvae. The gradient pointed one way. Larvae got smaller and smaller as the surveys moved southwest, and the smallest of all, some of them only around 9 millimeters. Animals so newly hatched they were barely anything, turned up in the southern Sargasso Sea, south of 30 degrees north and west of 50 degrees west, in an area centered near 26 degrees north and 60 degrees west, and predominantly in April and May. Schmidt published his conclusion in 1922. Every European eel and every American eel begins in the Sargasso Sea, and every one of them travels there to breed. Consider the migration that implies. An eel that has lived 20 years in a river in Ireland or Italy or Sweden changes its body, goes to sea, and swims thousands of kilometers across the open Atlantic, without eating, to a patch of water with no landmarks, no coastline, no seafloor feature within reach, no visible boundary of any kind, arriving in the right season to reproduce and die. Their larvae then drift back on the Gulf Stream and the North Atlantic Current, taking a year or more before turning into glass eels and finding their way into rivers on 2 continents. The thing that makes the still center useless to fishermen is exactly what makes it work as a nursery. No nutrients means no predators in quantity. A larva a few millimeters long, transparent, essentially invisible, drifting in nutrient-poor water, is far safer there than it would be in a productive coastal sea, full of things that eat larvae. Then the currents that bound the region do the transport, for free, in the right direction, over the right timescale. And here is what has not happened in the century since. Nobody has ever observed it. Not once. No European eel egg has ever been collected from the Sargasso Sea. No spawning adult European eel has ever been caught or seen there. The entire foundation of the accepted account is an inference from the size distribution of larvae, which is strong evidence, and it is still not observation. For decades, that gap was covered by the assumption that finding adults in that much water was simply a needle-in-haystack problem. Then people started tagging. Attempts to track eels through the open ocean go back to the 1970s, and they mostly failed because the tags were not up to it. Pop-up satellite archival tags changed that. They record depth, temperature, and light, stay attached for a programmed period, then release, float to the surface, and transmit their stored data to a satellite. In December 2018 and 2019, researchers released 26 large female European eels fitted with these tags from rivers in the Azores, chosen because the Azores sit partway along the canal in the migration and remove thousands of kilometers of uncertainty from the start of the journey. The tags reported for between 40 and 366 days. The animals moved at 3 to 12 kilometers a day, diving deep in daylight and rising at night, a vertical commute that appears to be about temperature and about avoiding being eaten. 6 of the tracked eels reached the boundaries of the Sargasso Sea. One reached the area believed to be the spawning ground. That result, published in 2022, was the first direct physical evidence that adult European eels actually arrive at the place Schmidt identified in 1922. 100 years to confirm the destination. The act itself remains unwatched. Nobody has recorded eels spawning. Nobody has photographed it. Nobody has collected the eggs. We know they go. We do not know, in any observed sense, what happens when they get there. There is a cost to that gap, and it is being paid now. The European eel has been listed as critically endangered by the International Union for Conservation of Nature since 2008. Recruitment, which is the measure of how many young glass eels arrive in European rivers each year, has collapsed. Depending on the index area and the year, arrivals are running at a few % of the levels recorded in the decades before 1980, and in some series, the figure is around 1%. The scientific advice from ICES has for years been zero catch, for every life stage, for every use, including the glass eels taken for restocking and for aquaculture. The causes are all human and all ashore or near shore. Dams and weirs that block migration routes, turbines that kill descending adults, habitat loss, pollution, parasites introduced through the trade in live eels, and an illegal export market in glass eels that is one of the most valuable wildlife trafficking flows in the world. And the reason this is so difficult to manage is the thing we have been circling. Every conservation measure in Europe is aimed at a life stage that happens in rivers. The event that determines whether there is a next generation at all happens in the middle of the North Atlantic, in water nobody governs and has never been observed. You cannot count a spawning you have never seen. You cannot protect a spawning ground whose boundaries you have inferred from the size of larvae in a net. which inverts everything the emptiness seemed to mean. The most barren surface water in the North Atlantic, the blue desert that starved sailing crews because it produced nothing to eat, is the origin point for the entire eel population of 2 continents. It is a nursery that has been running continuously for millions of years, in an ocean we have mapped from orbit, and the central event in it has never been seen by a human being. That is not romantic. It is a measurement problem, and it is the same measurement problem that has run through this entire story. This is a very large volume of water, and we can only look at tiny pieces of it at a time, which is exactly how we manage to lose track of something considerably less subtle than an eel. Since 1986, an organization called the Sea Education Association has been running sail training vessels across the western North Atlantic with undergraduates aboard, and part of the routine work on every cruise is towing a fine mesh plankton net behind the ship for half an hour and counting what comes up. It is unglamorous. Somebody streams the net, somebody times it, somebody logs the position, somebody sorts the catch under a lamp with tweezers. Over 22 years, those students ran more than 6,000 of those tows. In 2010, Kara Lavender Law and colleagues published what the accumulated dataset showed, and it did 2 things at once. The first was confirmation of something predicted but never demonstrated on that scale. More than 60% of the tows contained buoyant plastic, typically in pieces a few millimeters across, and the concentration was not evenly spread. It peaked sharply in a band across the subtropical North Atlantic, roughly between 22 and 38 degrees north, precisely where the Ekman convergence piles surface water into the center of the gyre. The theory said that floating material should accumulate there. 2 decades of nets confirmed it, in the same water and by the same mechanism that concentrates the sargassum. The second finding is the one that should stop you. Across those 22 years, global plastic production rose enormously. Consumption rose. Waste rose. Every input to the ocean that anyone can measure went up steeply. The concentration of plastic at the surface of the gyre did not increase. That is a mass balance problem, and it is not a comforting one. If far more plastic is entering the ocean every year, and the amount floating in the place where floating things collect has stayed roughly level, then the surplus is going somewhere that nobody is measuring. The candidate answers are all uncomfortable in different ways. Plastic at sea does not persist as bottles and bags. Ultraviolet light and mechanical stress break it into progressively smaller fragments, and once a fragment is smaller than the mesh of the net, it stops being data. It simply passes through and the count says it is not there. Biofouling is another route. Anything floating in seawater grows a film of bacteria, then algae, then small animals, and that added weight can sink a buoyant fragment out of the surface layer entirely. Animals eat it, and what they eat either passes through them and sinks in fecal pellets or stays in them. Storms mix the top layer down. Some fraction ends up in deep water and in seafloor sediment, which is where a growing amount of it is now being found. Whatever combination is responsible, the conclusion is the same. The surface is not the reservoir. It is the place things pass through on their way to somewhere we are not looking. Hold that next to the question this whole story started with, because it is the same answer arriving from a completely different direction. Why does wreckage never appear? Because this ocean gathers buoyant material slowly, disperses it locally, and then removes it from the surface layer permanently. That was an inference when we were talking about the Cyclops, built from the physics of convergence and the density of steel and ore. It is now a measured property of this water, established by 6,000 plankton tows across 2 decades, using an object far more abundant and far more persistent than a wooden hatch cover. The gyre takes things down. We have watched it do so with the most durable material human beings have ever manufactured, and we cannot account for the majority of it. The mats of weed and the plastic occupy the same windrows, which matters because those mats are not empty. Sargassum in the open Atlantic is a floating ecosystem, and it has residents that live nowhere else. The sargassum fish, histrio, is a frogfish camouflaged so exactly to look like a frond that you can stare at a clump for a minute and miss it. It has modified fins it uses to clamber through the weed like a small, ill-tempered climber. There is a sargassum crab, a sargassum shrimp, a sargassum nudibranch, all of them patterned in the same yellows and browns. Juvenile sea turtles spend years in this weed. The gap between a hatchling leaving a beach and a juvenile turtle reappearing in coastal waters is known as the lost years, and a good part of it is spent in sargassum mats out in the open ocean, hiding and feeding in the only structure available in 1,000 kilometers of open water. Those animals are now foraging in weed that is threaded with plastic fragments of exactly the size range that Convergence delivers there. And then, in 2011, the weed itself did something nobody predicted. Chuanmin Hu and Mengqiu Wang at the University of South Florida had been building a satellite record of floating sargassum, using the fact that vegetation reflects near-infrared light strongly enough to be picked out from open water by instruments in orbit. Their record ran back to 2000. For the first decade, it showed what everyone expected: sargassum in the Sargasso Sea and the Gulf of Mexico, drifting and dispersing, seasonally variable, staying broadly where it had always been. From 2011 onwards, a completely new feature appeared in the tropical Atlantic far to the south, in water that had never carried significant sargassum before. It kept coming back. By 2018, it had become the largest macroalgal bloom ever recorded. They named it the Great Atlantic Sargassum Belt. In June 2018, it stretched roughly 8,850 kilometers from the west coast of Africa across to the Gulf of Mexico, and the mass of weed in it was estimated at around 20 million tons. The mechanism appears to be nutrients, which is precisely the ingredient the Sargasso Sea does not have. Sargassum growing in the tropical Atlantic has access to discharge from the Amazon and to upwelling off West Africa that brings deep, nutrient-rich water to the surface. And in that environment, it does what any plant does when you feed it. It grows, and it fragments, and it grows again. And the equatorial current spread it across an entire ocean basin. The consequences land on people, and they land on shore. Sargassum arriving on a Caribbean beach in quantity is not seaweed on the sand. It is a mass sometimes a meter or more deep along the entire waterline, and it keeps arriving. It smothers seagrass beds and reef flats. It traps and kills turtles trying to nest or hatchlings trying to reach the water. It shuts down tourism, which is the economy of many of these islands, because nobody swims in it and the smell reaches the hotels. The smell is the health problem. As sargassum piles up and decomposes without oxygen, it releases hydrogen sulfide and ammonia. Hydrogen sulfide is the rotten egg gas. It is toxic, and at low concentrations it causes headaches, nausea, eye and respiratory irritation. Exposure among shoreline cleanup workers, the people who spend their working days shifting rotting weed with rakes and loaders, has been measured and studied specifically because those crews are getting the highest doses. Residents living along affected coastlines get chronic low-level exposure for weeks at a time. It also gets into infrastructure. Coastal power stations and desalination plants draw seawater for cooling and feedstock, and their intakes clog with weed. When an intake blocks on an island, the thing that stops is not a beach. It is electricity or fresh water. This would be the hardest thing in the whole story to believe if it were not photographed from orbit every week. For 5 centuries, the weed of the Sargasso Sea was the most overrated hazard in the Atlantic. It never held a ship. It never dragged anything down. It was a floating misdirection that made experienced sailors sound depths that had no bottom. It has finally become a genuine, documented, economically and medically serious hazard, and it did it 1,000 kilometers south of the sea that carries its name, by a completely different mechanism, and it does its damage on land. The sea itself is changing in a way that is measured better than almost anywhere in the world ocean. Because for more than 35 years, a ship has gone out from Bermuda every month to the same patch of water and lowered the same instruments. The Bermuda Atlantic Time Series study began sampling in October 1988. Every month, a research vessel goes to a station in the Sargasso Sea and works for several days, measuring temperature, salinity, oxygen, nutrients, carbon chemistry, particle flux, and the biology throughout the water column. It is the kind of program that produces nothing exciting for years and then becomes irreplaceable because you cannot go back and take a measurement in 1991. What the record shows is a surface that has warmed by roughly 0.85 degrees Celsius across the past 4 decades, and a rate that is not steady. That long-run figure averages in cooler stretches. Inside the single decade from 2010 to 2019, surface warming ran at more than a degree, faster than anything earlier in the series, alongside rising salinity, falling dissolved oxygen, and the steady shift in carbon chemistry that drives acidification. Now connect that to the machine we have been describing because it acts on it in 2 specific ways, and both of them make the existing system more like itself. A warmer surface layer sitting on cooler water below is harder to mix. Stratification strengthens. The boundary that keeps nutrients out of the sunlit zone becomes more resistant to being broken by winter cooling and storms, which is the one process that historically injected any nutrients into this system at all. A more strongly stratified subtropical gyre is a more oligotrophic gyre. The blue desert gets bluer, and the water gets clearer, and there is even less to catch. And a deeper reservoir of warm water is a better fuel supply for a hurricane. A storm crossing this region draws its energy from the heat in the upper ocean, and it undercuts itself by churning cooler water to the surface. The more warm water there is to churn through, the less a storm weakens itself as it passes. None of that creates a new hazard. It sharpens the 2 that have been operating here since before anyone was writing anything down. There is one more thing about this sea that is genuinely strange, and it is legal rather than physical. Nobody owns it. The Sargasso Sea sits almost entirely beyond the national jurisdiction of any state. Apart from the waters around Bermuda, it is high seas, which historically has meant that no single government has the authority to protect it, regulate what is taken from it, or control what is dumped in it. A sea with no coast has no coastal state. In March 2014, a group of governments signed the Hamilton Declaration on Collaboration for the Conservation of the Sargasso Sea, establishing the Sargasso Sea Commission. The initial signatories were the Azores, Bermuda, Monaco, the United Kingdom, and the United States, joined since by the Bahamas, Canada, the British Virgin Islands, the Cayman Islands, and the Dominican Republic. The Commission brings together those governments and independent scientists to keep the sea's condition under review. It is non-binding. It has no management authority. It is, in the most literal sense, a group of people agreeing to pay attention to an area of ocean roughly the size of a continent that nobody has the power to govern. So put the whole system together, because every piece of it has now been demonstrated rather than asserted. A permanent zone of high pressure sits over this part of the Atlantic and pushes air downwards, which kills the wind and suppresses the rain. The winds that circle it drive surface water inwards, which piles the middle of the ocean up by about a meter and forces water down, which pushes the nutrients out of reach of the light. That produces water of extraordinary clarity, with almost nothing living in it, which historically meant a becalmed crew could see 60 meters down and catch nothing, collect no rainwater, and watch their casks empty on a schedule they no longer controlled. The same inward drift gathers everything that floats, and then breaks it up, spreads it out, and sinks it, which is why a ship lost here leaves no case file. The only solid ground in the entire system is a small volcanic island wrapped in a reef that comes up out of deep water without warning, sitting directly under the track that Atlantic hurricanes take when they turn north. And that reef has both saved 150 people in a single act and destroyed more than 300 vessels. Human motive supplied the exposure at every stage. A colony that was starving, so the relief fleet sailed in hurricane season, a war that needed manganese. So an overloaded collier with one working engine left Barbados on schedule. A cargo of alcohol that had to reach Genoa, in barrels that were not all the same wood. A tired wooden ship that needed a shipyard in Florida, sailing on the day the forecast was worst. Technology changed the shape of the problem and never removed it. The chronometer fixed longitude and the reef stayed where it was. Steam beat the calm belt and carried ships into the emptiest water on the route. Radio meant you could call for help, and the Cyclops never got the chance to use it. Satellites made the hurricane visible days in advance, and the visibility made the passage look calculable. Every one of those improvements was real, and every one of them was spent on reach rather than banked as margin. And distance did what distance always does. It converted problems into emergencies. A cracked cylinder near a coast is a repair. A cracked cylinder 800 miles out is a ship that cannot maneuver. A parted tow line within sight of land is an embarrassment. A parted tow line 400 miles from the Azores is 10 people gone. A sinking 100 miles from Cape Hatteras is 14 survivors and 2 dead, because helicopters can get there and back. The same sinking 500 miles further east is a coordinator on a radio, waiting for a merchant ship to answer. Ships still cross it constantly because the great circle routes between North America and Europe, and between the Americas and Africa, run through and around it, and there is no alternative ocean. Yachts still cross it every season because the trade wind route to the Caribbean and the northern route home are exactly the circuit the Portuguese worked out 500 years ago, and it remains the sensible way to sail the Atlantic. Research vessels still go out from Bermuda every month. The eels still leave the rivers of Europe every autumn and swim out to a place we have confirmed they reach and have never watched them use. The final picture is not a storm. It is an office. Somewhere on Bermuda, a watchstander at the Maritime Operations Center takes a position report from a vessel in trouble a long way out and does the first thing anybody does: works out who can get there. That means a chart and a compass and a circle drawn around the nearest airfield at the radius a helicopter can fly out, hold a hover long enough to lift people off, and still get home with fuel in the tanks. It is a small circle on a very large chart. Then the plotted position goes on, and it sits outside the circle. The next call is to shipping, and the answer will be a name, a bearing, and a number of hours. Out where the casualty is, the barometer is high and steady. The sea is flat. The visibility is enormous, and the water is the clearest blue anyone will ever see. Nothing is moving on it except the weed, drifting slowly toward the middle, the way everything here does.